Hi there, my name is Ethan Weber and my teammate is Owen Seifried. Today we will talk to you about warm forging compared to hot forging and the possible advantages, limitations, and cost of the warm forging process. Furthermore, the presentation will conclude with a manufacturing readiness level assessment of the production method to determine if this process is applicable to our company. First, let's dive into some general background on warm forging. Warm forging is a relatively new method of forging that was developed in the 1950s or 1970s. The process involves heating a material to a temperature above the work hardening temperature and below the temperature where scale formation takes place. Due to this lower temperature, warm forging has been used for large-scale production in the automotive industry as the process yields closer tolerances and less shrinkage than traditional hot forging. To give an overview of this presentation, we will focus on the advantages, limitations, and cost of the warm forging process to determine its manufacturing readiness level. Then we will conclude while talking about the biases of the sources that we used for this video. I will be presenting the advantages and limitations of the process, while Owen will conclude the presentation with the cost analysis, manufacturing readiness assessment, and the bias assessment of our sources. So next, let's dive into the advantages of the warm forging process compared to the hot forging process. So for the advantages, the warm forging process involves the use of a medium temperature between the temperatures at which cold forging and hot forging take place. To be specific, is a temperature above room temperature and below the recrystallization temperature for the metal being forged. Because of the lower forging temperature when compared to hot forging, warm forging yields better tolerances than hot forging. This is because less shrinkage is observed and the lack of scaling on the part leads to less machining that must be done post-forging. The process can yield better surface finishes than hot forging, as well as a shorter manufacturing cycle time due to the lack of machining that must happen as a result of part shrinkage and oxidation. The warm forging process has been used for large-scale production in the automotive field. The Nissan Motor Company has released documentation of the warm forging process being used to reduce various automotive parts on a large scale. However, there are obviously limitations to the warm forging process that must be taken into account. So now let's talk about the limitations. In general, the warm forging process will need to use greater forging forces than the hot forging process. This is because the temperature of forging is less than that of hot forging, which will decrease the ductility of the part and increase the yield strength. As a result, tool life will be worse in warm forging as the tool is subjected to higher loads. This is a major concern for automotive manufacturers using warm forging in high production settings. Furthermore, much like hot forging, warm forging requires precise temperature control as to produce a part with specific tolerances and specifications. Because of this limited temperature range, the process of warm forging is also limited to specific materials that can operate at the medium temperature and can be formed at the medium temperature. The tools used in this method must be made to withstand the forming temperatures and also the higher press loads that are the result of a lower temperature. This means that significant engineering has to take place to design the proper tools, and precise care of the tool must be ensured to ensure maximum tool life. Finally, complex shapes are harder to manufacture using this method, as the lower temperature will increase the needed press load and decrease the formability of the forging material. These limitations have been explored in literature and are incredibly important factors in determining if this forging process should be used for our company. Next, Owen will provide a cost analysis of warm forging compared to hot forging and a manufacturing readiness assessment to determine if this process should be used for production within our company.
Next up is the cost. Looking at two main forging methods, we are comparing warm forging as more cost-effective of the two. Both have similar factors like material cost, labor cost, and energy costs, but where hot forging ends up costing more money is the power needed to run the machines and tools. The temperature range for warm forging to steel extends from above room temperature to below recrystallization temperature, but if you wanted a hot forge apart, the temperature would be larger than that of warm forging. You would be spending more money powering the equipment so that it can reach those higher temperatures needed to make the part than for warm forging. The tools used in forging are also a key factor when looking at the cost and manufacturing process. Warm forging deals with parts at lower temperatures, so the tools being used would be much less complex than those for hot forging. Hot forging needs much more complex tools because of the high heat environment they are in can wear and deform them over time. The part complexity for warm forging is much simpler than hot forging because you would need more heat to form a complex part, which isn't something you're trying to make if you want to use the warm forging method, unlike hot forging, where you are trying to form a complex part because of the added ductility that comes with the higher temperature. A final factor that makes hot forging less cost effective is the heat treatment and finishing it needs as a post process. In some cases, you may need to use a machine or apply coating to the part, which goes towards the cost of making a part. At the end of the day, one reason warm forging can be chosen over hot forging is because of its cost effectiveness when it comes to making metal parts. The manufacturing readiness process is a systematic review process that is used to evaluate the readiness of a manufacturing process for implementation at a specific production scale. The assessment is supposed to help identify risks, challenges, and areas of improvement before full-scale production. The first being technology readiness level. This essentially measures the level of technology we have based on what would be required for starting a warm forging part process, and it is given a rating on a scale of 1 through 9. The next step is the process capability. This evaluates the capability of the warm forging process to meet the required specifications for the intended part. This includes looking at the consistency of part dimensions, mechanical properties, and surface finishes. Our third step is checking the material readiness. This checks the availability and sustainability of the material we would be using for a warm forging process. Tooling equipment is what would be assessed next, and this would check to make sure the tools, dies, and molds and conditions of equipment were sufficient enough to work on parts that needed to be done by warm forging. We would need to make sure that the parts produced were consistent and showed no defects so that there would be a quality control and inspections part in our manufacturing readiness process. Like all manufacturing processes, cost analysis is a big factor. So having this in place lets us get an understanding of how much money it will cost and where the money is going. Supply chain readiness is another thing we took into consideration because making the part is one thing, but being able to have the materials sent in and out is another. Making sure the environment the process is happening in is safe, we included a regulatory compliance check to make sure safety measures are up to date. Risk management assessment is our ninth step that looks at the potential risk associated with warm forging, like technical risk and supply chain risk and market risk. After all this has been checked over, the final step is scaling up production. This assesses the feasibility of mass producing the part being made to see if they can meet the volume and demand required. After all this has been checked and given a score, we would determine if it was ready to be put into action and start the production process. Warm forging has been readily used in the industry already, with Nissan Motors using it specifically to create automotive parts. Based on documentation found in our research, much research is still to be done to figure out how to maximize tool life given the high temperatures and press load observed in the process. Therefore, the team has decided to give the forging process a manufacturing readiness score of 9 because the forging method has been used in production settings for automotive vehicles. The technology readiness level is rated at a 9 due to the fact that the technology associated with the method has been developed through both cold and hot forging, and the system has been tested and used in real production. Due to these ratings, the team concludes that warm forging process can be implemented into our company because the process is proving technological readiness and real-life production implementation. And finally, the team wanted to talk about the bias of the sources used for this analysis. The first source is a study done by Nissan Motor Company that talks about their use of warm forging process, its capabilities, and its downsides. Obviously, the source is biased towards the process as it uses the process in real-life production. However, the source is very transparent with emphasizing the capabilities and the downsides of the process, and therefore was deemed to be a reliable source for this presentation. Next, the Chisin Forging Company and Queen City Forging Companies were referenced. These two sites have bias because they're coming directly from forging companies. However, the two sites provide good information on the applications, upsides, and downsides of cold, warm, and hot forging process to compare the processes. The source summarized their information into figures with advantages and disadvantages to highlight the reason for the article. These sources were deemed to have little bias as the source provides applications, upsides, and downsides to cold, warm, and hot forging and seem to have little motivation for selling a specific process. Finally, the last source used was the manufacturing readiness level document provided on Canvas. This document has little to no bias as it provides information of the MRL process and how to properly assign a ranking to the production process. This source was used merely to identify the MRL for warm forging and did not provide any motive for or against the process. Therefore, the team concluded that all of our sources dealt with production and real-life manufacturing with little to no bias for or against our process.